Welcome back to the deep dive.
Hmm.
Today we are tackling something that I think a lot of people mistakenly view as just a dry technical manual.
Oh, absolutely.
But when you really start to peel back the layers, it looks a lot more like a philosophical treatise on how humans should, interact with machines.
That's a great way to put it.
We are digging into a massive stack of notes and research centered around learning Python. And we're specifically focusing on the context of the fourth edition of the seminal book by Mark Lutz.
It's good to be back. And you're so right, to call this just a coding manual is to completely miss the forest for the trees. When we went through all the source material, what really stood out to me wasn't just the syntax.
Right, not just where the semicolons go or something.
Exactly. It wasn't about how to define a function. It was the underlying ethos, the whole spirit of the thing. We're looking at a language that made a very specific and I'd say very bold bet.
Okay, what was the bet?
The bet was that the most expensive resource in computing isn't the processor speed. It's not the memory. It's the programmer's brain.
Which is such a fascinating pivot from, the entire history of computing up to that point.
It's complete 180.
And we have a lot to cover today. We're going to look at why this language, which I believe started as someone's holiday project,
It did, yeah. A side project.
ended up powering everything from the back end of YouTube to the guidance systems at NASA. We're also going to break down the Perl versus Python culture war, which the text goes into quite a bit.
Oh, it does. That was a real holy war in the 90s.
And ultimately, we're going to try to answer the question of why a language that is technically slower than its competitors became the dominant force in modern engineering.
That speed versus productivity equation is really the heart of the matter. It's the central question.
Absolutely. And for you listening, maybe you're sitting there thinking, I'm not a coder, why should I care? Well, the promise of this deep dive is efficiency. The source material claims that Python code is typically 1/3 to 1/5 the size of equivalent C++ or Java code. So even if you never write a single line of code, understanding how that efficiency is achieved tells you a lot about how modern software is built and why your apps work the way they do.
It really changes the economics of software development. I mean, think about it. If you can build a product in 2 months instead of 10, that's not just a technical difference.
No, that's a business model revolution.
Exactly. It's the difference between a startup getting funding or going bust.
But before we get into the heavy engineering and all the economics, we have to address the elephant in the room, or maybe the snake in the room.
I see what you did there.
Because names matter, don't they? When I hear Python, and I think most people are the same, I immediately think of a boa constrictor, something predatory. It sounds aggressive.
It does sound like a weapon or, a predator. And if you look at the classic O'Reilly books, they really lean into that. They've got the woodcut illustrations of all these different snakes on the covers.
Right, so you just assume.
You assume. But the origin story is completely different, and frankly, it explains so much about the community and the whole vibe of the language.
It's not a snake.
It is not a snake. Guido van Rossum, the creator of the language back in the late 80s, was a massive fan of Monty Python's Flying Circus.
The British comedy troupe. No way.
Yes. The story goes he was reading their published scripts while he was developing the language over the Christmas holiday, and he just needed a name that was short, unique, and just a little bit mysterious. So he picked Python.
Which, on the surface, seems like a trivial detail. Bit of trivia for a pub quiz.
Yeah.
But the source material strongly suggests this actually bled into the design philosophy itself.
It did, in a huge way. You have to understand, computer science, especially back in the 80s and 90s, was an incredibly serious place. It was academic, it was rigid, and let's be honest, it was often quite dry.
Very dry.
By naming the language after a surrealist comedy sketch show, Van Rossum signaled something really important from day one. He was saying, we are not going to take ourselves too seriously here.
And the text points to the tutorial examples as proof. In a standard computer science class, you learned about variables using these placeholder names like foo and bar.
Right, which are these meaningless military slang terms from World War II. They're placeholders for anything.
Foo-bar.
Right. But in Python documentation, and this is consistent across decades, it's in the official tutorials to this day, the examples use spam and eggs.
Referencing the famous Monty Python sketch where everything on the menu at the Greasy Spoon Cafe comes with spam.
Spam, 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 and spam. Exactly. And while that's funny, it actually serves a very real purpose. It lowers the barrier to entry. It tells the learner, relax, you're allowed to have fun here, you're allowed to play.
It's a psychological signal.
It's a huge psychological trick, yeah. It positions the language as approachable rather than intimidating. And that subtle choice of tone, it sets the stage for the entire ecosystem that grew up around it.
So, we have a language rooted in comedy, but it's being used for incredibly serious things. Let's dig into that philosophy section from our notes. The source material spends a good amount of time contrasting Python with Perl. Now, for the non-programmers listening, Perl was the absolute king of scripting in the 90s.
Oh, undisputed. If you were building the early web, you were almost certainly using Perl.
So how does the text describe this rivalry? It wasn't just two different tools, was it?
No, it was a clash of cultures. The book frames it as a battle between art and engineering, and it's a really, really useful distinction.
Okay, so Perl is art.
Perl is described as art. Its official motto, and they were very proud of this, is there's more than one way to do it. Or Tim Tao TDI, as they'd say.
This sounds liberating. I mean, that sounds good, right? Express yourself however you want.
It is incredibly liberating for the person writing the code. It allows for this incredible, concise, clever, almost poetic style of programming. You can write a script in Perl that does 5 different things in one line of cryptic symbols. It's like a puzzle.
I see the problem already.
You see it, right. The problem is, software isn't just written, it has to be read.
Right. Someone else has to come along later and figure out what you did.
Exactly. If you hand that artistic Perl script to another programmer, or let's be honest, even to yourself 6 months later, it can look like line noise. It's unrecognizable. You have to spend hours, sometimes days, just decoding the art to understand the basic logic.
So Python then takes the complete opposite stance.
The complete opposite. Python is engineering. Its underlying philosophy, which isn't an official motto but is repeated everywhere, is usually summarized as there should be one, and preferably only one, obvious way to do it.
That sounds so restrictive. It sounds like the fun police showed up.
It is restrictive, but it's intentionally so. It's a productive constraint. It forces everyone to sing from the same song sheet. If I look at your Python code, it's going to look almost exactly like my Python code. The structure is predictable. The style is predictable.
The source material uses the phrase explicit is better than implicit. I think that gets to the heart of it.
That's the golden rule. It's from a document called The Zen of Python. Don't do magic behind the scenes. Make it absolutely clear what is happening at every step. This all serves the god of readability.
And the text argues that code is read significantly more often than it is written.
Orders of magnitude more. You might write a function once in an afternoon, but that function might be read by 10, 20 different engineers over the next 5 years as they try to fix bugs or add new features. Python optimizes for them, for the readers, not for the original author's vanity or their desire to be clever.
There's a great phrase in the notes I liked. Python syntax fits your brain.
That's a great way to put it. It's because Python uses indentation, literally the white space on the page, to define blocks of code.
Instead of curly braces or keywords like end.
Exactly. So it ends up looking like a well-formatted document or an outline. It looks like the pseudocode you'd write on a whiteboard before you even start coding. You don't have all these curly braces and semicolons and other symbols cluttering up the visual field. It reduces the cognitive load.
And when you aren't fighting to just parse the syntax, you can focus entirely on the logic of what you're trying to build.
You're solving the problem, not fighting the tool.
But this focus on readability and human friendliness, I mean, there has to be a cost, right? In engineering, you never get something for nothing. If the computer's doing all this extra work to make things nice for me, isn't the computer itself working harder?
You've hit on the classic, and for a long time, the most effective critique of Python. The cost is raw execution speed.
It's slower.
It is slower. Python is an interpreted language. Now, we'll get into the weeds of what that means later, but essentially it means there's a layer of software, the interpreter between your code and the hardware. A language like C or C++ compiles directly to machine language. It talks straight to the chip. So instruction for instruction, C is always going to be faster.
So if I'm writing, say, a high-frequency trading algorithm where I need to execute a trade in microseconds to beat the market, Python is probably a bad choice.
In that specific hyper-optimized scenario, yes, pure Python might be too slow for the absolute core logic, but the source material makes a counter-argument that is really the defining logic of the entire modern software industry. It asks a simple question: what is expensive?
And the answer used to be computer time, the hardware.
Right. In 1970 or even 1990, CPU cycles were precious. Memory was measured in kilobytes. You had to optimize your code to save every millisecond because the hardware was slow and unbelievably expensive. Today,
you can rent a supercomputer in the cloud for a few dollars an hour.
Exactly. Hardware is cheap and abundant and ridiculously fast. What's expensive today?
The engineers?
The people. The people. An hour of a senior developer's time costs a fortune. So, the Python philosophy is this. Let's optimize for the developer, not for the machine.
Get the product out the door faster.
If I can write a program in Python in 2 hours that would take you 2 days to write in C++A, I win. The business wins. It doesn't matter if my program takes half a second to run and yours takes a millisecond. In 99% of applications, the user will never notice that difference. But the business will absolutely notice getting a feature 2 days earlier.
But there has to be a limit, right?
Yeah.
At some point, the program is just too slow, and the user does notice.
Yeah.
The app feels sluggish.
Of course. And this is where the genius of Python's design comes in. The strategy is called optimize later.
So don't worry about it up front.
Don't even think about it. The text explains that Python is designed to integrate seamlessly with C. So you write the whole system in Python first because it's fast to build and easy to change. Then you profile it. You run tests to find the one little part of the code that is the actual bottleneck.
And it's usually just one small part, isn't it? The 80-20 rule.
It's almost always a tiny loop somewhere that's doing 90% of the work. So you find that one bottleneck.
And you rewrite just that one part.
You rewrite just that one tiny piece in C, compile it, and then you import it back into Python as if it were any other module. Python acts as the glue. So you get the development speed of a high-level language for 99% of your code, with the raw execution speed of C right where it actually matters. It's the best of both worlds.
Let's talk about what this language actually is then. Because there is this term that keeps popping up in the text, scripting language. And it feels like the author is a bit defensive about it, like it's a dirty word or something.
It's a very loaded term. For a long time, in the hierarchy of programming, scripting was looked down upon. It implied something simple, maybe even trivial.
Like a task for an intern.
Exactly. A script was something you wrote to automate a file backup or rename a bunch of folders. It wasn't considered real programming, like building a database or an entire operating system.
The text mentions 3 different common definitions for scripting. The first is shell tools, which is that automation piece you just mentioned.
Right, and Python is fantastic at that. It can talk to the operating system, it can move files, it can read text patterns, run other programs. It's a great replacement for shell scripts.
The second definition is control language, the glue.
This is a huge, huge use case. Imagine you have a massive pre-existing library written in C++ that does incredibly complex mathematical simulations. It's powerful, but it's a nightmare to use directly. You can wrap that C++ library in Python. So the user, maybe a scientist, writes simple, readable Python commands, but Python just delegates the heavy lifting to the C++ engine underneath. It controls the other, more complex language.
And the third definition is just ease of use.
Which is where the stigma comes from. People, especially in the old guard, assume that if it's easy, it can't be powerful. But the source material really fights back against this idea. It defines Python as a general-purpose, object-oriented language.
So it's trying to reclaim the term.
It's arguing that while Python can be used for scripting, calling it just a scripting language is like calling a Ferrari a grocery getter just because it happens to have a trunk.
And to prove that point, the text starts dropping some heavy names.
Yeah.
We mentioned Google and NASA in the intro, but I want to dig into why they use it. Take Google. The notes say they use Python for their web search systems. Now, Google is a company that is obsessed with speed. Why would they use a supposedly slower language for something as critical as search?
You have to think about the environment in the early days of Google. They were in a race with AltaVista and Yahoo. The web was exploding. The structure of the internet was changing daily, hourly. They needed to iterate incredibly fast.
They needed to be agile.
Supremely agile. If they wrote their web crawling logic in C++ Wick, every time they wanted to change how they indexed a new kind of web page, they'd have to rewrite complex memory management code, recompile everything, debug for days. It's a very slow development cycle.
And with Python?
With Python, they could change the logic in the morning, test it in a safe environment, and deploy it by the afternoon. The productivity over execution speed bet paid off in spades for them. They could out-innovate their competitors because their tools allowed them to move faster. The source also mentions Google's App Engine.
Which were their cloud platform, right?
Yeah, one of the first big ones. It basically let other developers use Google's infrastructure to build their own apps, and that was originally built entirely around Python.
Okay, what about the other end of the spectrum? Not fast-moving web companies, but hard science. NASA, Los Alamos, the Jet Propulsion Laboratory.
This is a totally different driver. Scientists are, for the most part, not trained software engineers. They're physicists, they're astronomers, they're biologists.
They're domain experts.
Exactly. They know the math inside and out, but they don't want to spend their lives debugging C++ syntax errors or managing memory pointers. That's a distraction from their real work.
You just want a tool that works, a tool that lets them do their science.
They want a calculator that can handle petabytes of data. Python fits that engineering mindset perfectly. The code often reads like the mathematical formulas they're trying to implement. Plus, the ecosystem of scientific libraries, things like NumPy and SciPy, allows them to crunch massive numbers with incredible efficiency because those libraries are themselves written in C and Fortran.
So it's that glue concept again.
It's the ultimate glue. The scientist writes clean Python, and the interpreter calls down to super-fast, decades-old compiled code to do the actual number crunching.
I found the mention of ILM and Pixar really interesting, too. Industrial light and magic. We're talking about movies like Star Wars and Jurassic Park.
Right. Computer graphics is an incredibly complex field, but the day-to-day workflow is very iterative. An animator needs to tweak the position of a lighting rig, generate a preview of the scene, see how it looks, and then do it again 100 times.
They can't recompile a universe every time they move a light.
No way. Python is used to automate those pipelines. It's the scripting language inside the big 3D applications. It manages the thousands of assets that go into a single shot. Again, it allows the artists to be artists without getting bogged down in the technical assembly line.
It seems like the common thread here is that Python handles the boring, repetitive, and error-prone stuff, so the human can focus on the interesting, creative, or scientific stuff.
That's a perfect summary. It's a force multiplier for human intellect.
And speaking of handling the boring stuff, the text highlights two key technical features that make all this possible: dynamic typing and automatic memory management. Now, to a layperson, those sound like pure jargon. Can we break those down?
Let's try. Let's start with dynamic typing. In a static language like C or Java, you have to be incredibly rigorous up front. If you want to create a variable to hold a number, you have to formally tell the computer, I am declaring a variable, its name is X, it is an integer, and it will only ever hold an integer for its entire life.
It's like buying a Tupperware container that is only shaped for a very specific size of sandwich.
That's a great analogy, and if you try to put soup in that sandwich container.
The compiler screams at you and the program refuses to even run.
Exactly. In Python, you just say x equals 5. Python looks at that and says, okay, 5 is a number, so for now, x is holding a number. A line later, you can say x equals hello. Python just says, okay, no problem, now x is holding a string of text.
It adapts on the fly.
It adapts. The type belongs to the object itself. The number 5, the string hello, not to the variable name, x. This removes a massive amount of what programmers call boilerplate code. You don't have to declare everything up front. You just write the logic you care about.
Okay, that makes sense. Now, what about the second one? Automatic memory management.
This is the big one. This is arguably the single biggest productivity booster. In the old days, with C or C++C, if you created a big list of 1 million items in your program, you had to manually ask the computer's operating system for a specific chunk of RAM to store it.
Okay.
And this is the critical part. When you were finished with that list, you had to manually write code to give that RAM back to the system.
And if you forgot to do that?
That's called a memory leak. Your program just eats up more and more RAM every time it runs until eventually the entire computer slows down, freezes, or crashes. And finding those leaks is an absolute nightmare.
So how does Python handle it?
Python has a built-in garbage collector. You can think of it like a little robotic janitor that runs in the background of your program. It uses a system called reference counting. It looks at every piece of data in memory and asks the simple question, is any part of the program still using this? If the answer is no, if there's 0 references pointing to that data, the garbage collector automatically sweeps it up and reclaims the memory.
That sounds incredible, but I have to play devil's advocate again. If there is a janitor constantly running around in the background checking all my data, doesn't that take up processing power? Isn't that an overhead?
It absolutely is. That is part of the cost that makes Python execution slower than C. In C, you are the janitor, so it's very efficient, but it's exhausting and you're prone to making mistakes. In Python, you hire a janitor. It costs a little bit in performance, but it saves your sanity and prevents a huge class of bugs.
I like that analogy a lot. You're trading a few CPU cycles for your own sanity.
It's almost always a good trade to make.
Let's shift gears a bit to the historical context of this specific source material. We're looking at the fourth edition of Learning Python, and as you mentioned, it sits at a very weird and very important moment in the language's history. The text talks at length about a split between Python 2.6 and Python 3.0.
This is the tale of two pythons. And it's a fascinating and I think cautionary case study in software governance and community management.
So what was the situation?
By 2008, Python had been around for nearly 20 years. And like any project that runs for that long, it had accumulated, well, cruft, warts, inconsistencies, design choices that seemed like a good idea in 1990, but with 2 decades of hindsight, turned out to be mistakes. There were duplicate ways to do some things, which went against the core philosophy.
The one obvious way to do it, philosophy, was getting muddy.
It was getting very muddy, so Guido and the core developers decided to do something incredibly brave and also incredibly dangerous. They decided to clean house. They released Python 3.0.
And the goal of 3.0 was to fix these flaws.
Yes, but to properly fix them, they had to break backward compatibility.
Explain the danger there. That sounds significant.
It's a cardinal sin in software development. Usually when you upgrade software, say you go from Windows 10 to Windows 11, all your old apps are supposed to still work. If they didn't, nobody would ever upgrade. Python 3.0 made a different choice. It essentially said, code written for Python 2 will not run here. It's a new world.
That sounds like a disaster waiting to happen. If I'm a company with 1 million lines of working Python 2 code, I can't just flip a switch and upgrade.
You can't. You're stuck. And that created a massive rift in the community that lasted for over a decade. This book, the 4th edition, had to cover Python 2.6 and 3.0 simultaneously because that was the reality on the ground.
And what was 2.6?
2.6 was meant to be the bridge. It was the last major version of the old Python 2 line, but they backported some of the new features from 3.0 and added warnings about the old features so people could start preparing their code bases for the eventual migration.
What were some of the actual changes that caused this break? The text mentions the print statement as a classic example.
It's the one everyone points to. In Python 2, to print something to the screen, you just typed print hello. It was a special statement, a command built into the language.
Correct.
In Python 3, they decided print should be a function, just like everything else in the language, for consistency. So you now have to type print hello with parentheses.
That seems trivial. Why break the entire language and split the community for a decade over a pair of parentheses?
It seems trivial on the surface, but it's about that core principle of consistency. If print is a function, you can do things with it that you couldn't before. You can pass it as an argument to other functions. You can assign it to a variable. It fits the engineering philosophy better. But yes, from a practical standpoint, it meant that millions of existing scripts would suddenly produce syntax errors if you tried to run them with Python 3.
And the notes mention this created a dilemma for the learner at the time. Which one do you learn?
The advice was incredibly tricky back then. The book says if you were starting a brand new project from scratch, you should use 3.0. That was clearly the future of the language.
What?
But if you wanted to use any of the thousands of existing libraries for web development, for game engines, for scientific computing, they were almost all still written in Python 2 and hadn't been updated yet. So to do any real work, you had to know Python 2.
It's like the analogy we discussed earlier, learning Latin to understand French. But in this case, the office next door is still actively speaking Latin.
And loudly refusing to stop speaking Latin. It took years and years for the major libraries to finally port their code to Python 3. Today, thankfully, we're finally all on Python 3, but this book really captures that moment where the community was standing on a precipice looking at 2 different paths forward.
Let's go a layer deeper then. We've talked a lot about the code itself, but we haven't really talked about what happens when you hit run. To most people, that's just a black box, but the source material breaks down the interpreter model in a lot of detail. It talks about things like bytecode and the PVM. I think we need to demystify this.
Let's open up the black box. It's actually not as scary as it sounds. When you write a Python script, you're just creating a simple text file that ends in .py.
Right.
When you tell the computer to run that file, the very first thing that happens is a step called compilation.
Wait, you're going to have to stop me there. I thought you said Python was interpreted, not compiled.
It's a common point of confusion. It's a nuance. It doesn't compile all the way down to the binary machine code that your CPU understands directly. It compiles to an intermediate format called bytecode.
Bytecode code.
This is a low-level, platform-independent set of instructions. If you've ever seen those .pig files that seem to appear in your folders after you run a script.
Yeah, I've seen those. I usually just delete them because they look like clutter.
Don't delete them. That's the compiled bytecode. Python saves it there for a reason. And the reason is startup speed. The next time you run your program, Python is smart. It checks the timestamp of your .py source file and the .py bytecode file.
And if the source code haven't changed?
It skips the compilation step entirely and just loads the precompiled .py file. It makes the program start up just a little bit faster. It's a small optimization, but it adds up.
Okay, so we have this bytecode. It's not English, and it's not the machine's native language. What actually reads it and runs it?
That is the job of the PVM, the Python virtual machine.
This is the concept I always struggle with. Is it a real machine? Is it a program? A simulation?
The best way to think of the PVM is as a software CPU. Your physical computer chip, your Intel or ARM processor, speaks a very specific language, by86 or ARM assembly. Python bytecode doesn't speak that language. It speaks its own generic language called Python.
So the PVM is the translator.
It's the translator. The PVM is a big piece of software that essentially sits in a loop. It reads one instruction of bytecode, instantly translates that instruction into whatever language your physical CPU understands, and tells the CPU to execute it. Then it moves on to the next bytecode instruction and the next, and so on.
So it's like a universal translator from Star Trek.
That's a perfect analogy. And this is the key to why Python is so portable.
Meaning I can take the same script and run it on Windows, on a Mac, or on a Linux server.
Yes. Because your .p script and the bytecode it produces are the same everywhere. You just need a different PVM, a different translator for each machine. The PVM for Windows knows how to talk to the Windows kernel. The PVM for Mac knows how to talk to the macOS kernel. Your code just floats above all that mess, blissfully unaware of the hardware it's actually running on.
That explains the old write once, run anywhere slogan.
It does, but it also helps explain the different flavors of Python that the text mentions. The standard one that almost everyone uses is technically called CPython.
Why CPython?
Because the PVM itself, that translator program, is written in the C programming language.
But there are others.
There are. The book talks about Jython.
Which I'm guessing is Python for Java.
You got it. It's a completely different implementation of Python where the PVM is written in Java. And what it does is it compiles your Python source code not to Python bytecode, but to Java bytecode.
So it runs on the Java virtual machine, the JVM.
Exactly. This means you can write Python scripts that run inside a larger Java application, and they can interact with Java objects as if they were native Python objects.
That sounds like a very specific kind of magic for a very specific audience.
It's incredibly useful for large corporate environments that have a huge investment in Java infrastructure, but want the flexibility and speed of Python for scripting and extending their systems. There's also IronPython, which does the same thing for Microsoft's .NET framework, integrating with languages like C#.
So Python is like water. It just takes the shape of whatever container you pour it into.
That's a beautiful way to put it. It's designed to be embedded and to be a glue language.
There's one more execution concept I want to touch on from the notes, because it has a really big business implication. The idea of frozen binaries.
Right. Because here's a practical problem. If I write a cool game in Python and I want to send it to you to play, I can't just email you the .py file.
Why not?
Because you might not have Python installed on your computer. Or you might have the wrong version of Python. Or you might not have the specific libraries I used to build the game. It just won't run.
So you're saying I have to be a developer myself just to run your code? That's a terrible user experience.
It's a non-starter. Frozen binaries solve this problem. There are tools, like PyInstaller, that take your script's bytecode, bundle it together with a mini version of the PVM and all the libraries your code needs, and then wrap it all up into a single, standalone executable file, like a .exe file on Windows.
So I just get an icon I can double-click like any other application.
You just double-click it and it runs. You, the end user, have no idea it's Python. You don't know there's a virtual machine running inside of it. It just looks and feels like a normal native program. This is how most commercial software that's written in Python is distributed to customers.
Okay, so we've covered the engine in painstaking detail. Now let's talk about how to actually drive the car. The source material has a great section on practical execution, and it starts with the most fundamental tool, the interactive prompt.
The famous 3 arrows, the prompt.
Describe that experience for someone who has maybe never seen it before.
You open your computer's terminal or command prompt. You just type the word Python and hit enter, and you get this prompt. You are now in a direct, live conversation with the Python virtual machine.
So you can just type commands.
You type a line of code, say 1 + 1, and hit enter. The interpreter immediately evaluates it and prints the answer on the next line.
2. It seems almost too basic.
It is basic, but it is profound. In a language like C++A, to check if 1 plus 1 equals 2, you'd have to write a whole file, include some library headers, write a main function, compile it, link it, and then finally run it. It would take minutes. In Python, it takes a second. This encourages experimentation.
So if I'm not sure what a command does, I can just try it out right there and see what happens.
Exactly. The text encourages you again and again, fire it up and type it. It turns learning from a purely theoretical exercise into an empirical, scientific one. You poke the beast and you see how it reacts.
But there are some traps for beginners here. The notes mention the prompt change.
Yes, the dots. This confuses every single beginner, without fail. If you type a line of code that requires more lines to be complete, like an if statement or a for loop, you'd type for X in my list. And you hit enter.
What happens?
The prompt changes from to S.
What do the dots mean?
It means Python is waiting. It knows you aren't done yet. It's waiting for the indented block of code that goes inside the loop. The trap is that when you are done writing that block, you have to hit a no-bow, enter on a blank, empty line to tell the interpreter, okay, I'm finished. Execute the whole block now.
And beginners just sit there staring at the dots.
They sit there staring, wondering why nothing is happening. It's a standoff. The computer is politely waiting for you to finish your sentence, and you're waiting for the computer to reply.
Another practical issue that the book mentions is for Windows users specifically, the clicking icons problem.
The infamous flash.
Walk us through it.
Okay, so you write your very first script, the classic print, hello world. You save it as hello.p on your desktop. You are so proud of yourself. You double-click the icon. A black window pops up on screen for a split second and then vanishes instantly.
And you think it crashed? Or your computer is broken?
You think something went horribly wrong. But no, it did exactly what you told it to do. It opened a DOS console window, it printed the words hello world to that window, and then, since there were no more instructions in your script, it finished and closed the window. The whole process probably happened in less than 100 milliseconds.
So you never even had time to see your message?
You never saw it. The fix for this is a classic hack. You add one more line at the very end of your script. Input.
What did that do?
The input function tells the program to stop and wait for the user to type something on the keyboard and press enter. So now the program prints hello world, and then it just pauses with the window open, waiting for you. The window stays open until you finally hit the enter key.
It feels like such a simple, almost silly workaround, but I bet that has saved millions of hours of frustration for beginners.
It's a rite of passage for every Windows Python programmer.
The text also introduces something called IDLE, the Integrated Development Environment.
IDLE is basically the official training wheels for Python. It comes installed with Python by default. It gives you a text editor that understands Python, so it has syntax highlighting, keywords are orange, strings are green, and so on. It helps you visually parse the code much more easily than a plain text editor.
But it's not what the pros use.
It's great for learning, but it has some quirks. The text warns about save issues. Sometimes you have to remember to manually add the .py extension when you save a file. And because IDLE itself is written in Python using a GUI library called Kinter, trying to run other advanced graphical programs inside of IDLE can sometimes cause weird conflicts. It's like the snake eating its own tail.
Let's move to the final and maybe most important piece of the technical puzzle. The outline calls this the aha moment, section 6, the architecture of modules.
This is really where we graduate from writing simple single-file scripts to building complex multi-file systems.
So what exactly defines a module in Python?
It's deceptively, almost shockingly simple. Any file ending in .pyr is a module. That's it, the whole definition.
So I don't have to write module X starts here at the top of the file or anything?
Nope. The file name is the module name. If you have a file named database.py, you have a module named database. And this immediately introduces the concept of namespaces, which is absolutely crucial for keeping large programs organized.
Okay, explain namespaces with an analogy.
Imagine you work in a large office building. There might be a person named David in the accounting department and another person named David in the engineering department. They both have the same name, David, but there's no confusion because they exist in different departments.
The departments are the namespaces.
The departments are the namespaces. In Python, if I have a file named math.py, any variable or function I create inside that file belongs to the math namespace. If I have a physics.py file, its variables belong to the physics namespace. So both files can have a function named calculate without them ever colliding with each other.
And to access them from another file, I use the import statement.
You'd write import math. Now, in your code, you can say math.calculate. You are explicitly stating which department's calculate function you want to use.
But there is another way, the from statement, as in from math, import calculate.
This is where it gets a little more convenient, but also a little more risky. From math, import calculate is like telling David from the accounting department to come out of his office and stand right next to you at your desk. Now, you can just call him David or calculate directly without mentioning his department.
But what if I already have a coworker named David standing at my desk?
Then the new David from accounting silently replaces the old one. You just overwrote your variable or function, and you might not even realize it. This is why the explicit is better than implicit. Philosophy generally prefers the import math style. It keeps the namespaces clean and avoids accidental name collisions.
There is a very specific and very important technical detail about how imports work that the text highlights, the concept of run once.
This is a huge gotcha for beginners and even intermediate developers. When you type import math, Python finds the mal.py file and executes all the code inside it from top to bottom. But it only does this the first time you import it.
Why only the first time?
It's an efficiency thing. If you import math in 10 different files throughout your program, you don't want Python to have to reload and recompile and rerun that whole file 10 separate times. That would be very slow. So it loads it once, caches the resulting module object in memory, and then just reuses that cached version for all subsequent imports.
But what if I'm a developer and I'm actively working on the math module? I find a bug, I change the code, I save the file, and then I try to run my main program again to test the fix.
If you're running in an interactive session or a long-running server application, simply typing import math again does absolutely nothing. Python sees that math is already in its cache, and it just uses the old cached version. You won't see your changes.
That sounds incredibly infuriating.
It is one of the most frustrating experiences when you're starting out. The solution is that you have to explicitly use the reload function. You'd have to type reload math. This forces Python to discard the cached module and read the file again from the disk, executing your new code.
And this is where the Python 2 versus Python 3 version split comes back to bite us one last time.
Yes, it does. In Python 2.6, reload was a built-in function. It was always available right there for you to use. In Python 3.0, as part of the language cleanup, they decided that dynamic reloading was a bit of an advanced and potentially dangerous feature, so they move it.
They made it harder to get to.
They did. You now have to first import importlib and then call importlib.reload. The implicit message from the language designers was, you probably shouldn't be doing this. If you are changing your code, the safest and cleanest thing to do is just restart your whole program.
It's the computer equivalent of the classic tech support line. Have you tried turning it off and on again?
Precisely. It's the clean slate approach. Start fresh so you know exactly what state your program is in.
We have covered a truly massive amount of ground here. From the comedy of Monty Python to the intricacies of memory management, from the 2.6.3.0 Civil War to the inner mechanics of the Python virtual machine. When you step back and look at this entire deep dive, what's the synthesizer? What is the one core takeaway you think people should remember?
For me, it all comes back to that initial philosophy we talked about, empowerment. Python, as a technology, is fundamentally designed to get out of your way.
That idea of engineering over art.
But specifically, it's a kind of human-centered engineering. It's a tool that acknowledges that programming is a human activity. It acknowledges that we humans have limited memory, we make typos, we get confused by overly complex syntax, and Python, at every turn, tries to smooth over those rough edges.
It shifts the burden of complexity.
It absolutely shifts the burden
Right.
from the human to the machine. The language says, I will handle the memory management, I will handle tracking the data types, I will handle the platform differences. You just focus on your idea. You focus on the problem you're trying to solve.
And that really explains the incredible breadth of its adoption. That's why a scientist at NASA can use it to find a new planet, and at the same time, a teenager can use it to make a simple Discord bot.
It democratizes the power of computing. It's a tool that scales all the way from a 5-line script to a 5 million-line application without the core principles ever really changing.
I think my favorite detail out of all of this is still that experimentation aspect. The idea that the language itself, through the interactive prompt, invites you to play with it.
That is the secret sauce. It really is. It removes the fear of failure. You try something, it gives you an error. You try something slightly different. It makes the process of learning a tight interactive loop rather than a terrifying cliff you have to jump off.
And I want to leave you, the listener, with a thought that really struck me while reading this section on bytecode and the PVM. We are sitting here typing what are essentially English words, print, if, import.
We're writing text.
Just characters in a file, but that text controls a virtual machine, which is itself a simulation running on a real machine. And that simulation is controlling the flow of electricity through physical silicon, switching billions of transistors on and off every second.
We are so many layers of abstraction removed from the physical reality of the computation.
We are. But thanks to tools and philosophies like the one behind Python, we have more control over that reality than ever before. We can wield all that power without needing to understand the quantum physics of a transistor.
That is the beauty of abstraction. And Python is, in my opinion, one of the most effective and elegant abstractions we've ever built as a species.
Well, I think that's a perfect place to wrap things up. I'm going to go open a terminal and type import this.
Ah, the zen of Python. A perfect Easter egg to end on.
Exactly. Thanks for listening to The Deep Dive. We'll see you next time.
Happy coding.